First of all, I would like to thank the organizers for giving me this opportunity to present some of the recent work that I have been doing. And so yes, today I'll talk about activity-driven transport in harmonic systems, which is a joint work done with Urna Basu from Shotenbosch Center, Kolkata. And it will basically be on these two papers. It will mostly be on the first paper, and I'll briefly mention about the second one. Okay, so let's begin with transport. So transport in particular is something which is known to us all, thermal transport, or more in particular thermal conduction, heat conduction. So, I mean, people have been interested in heat conduction problems for a long time. So the basic picture is like you have a hot reservoir and a cold reservoir, and you connect it with some conductor, like a conducting wire or something, and then people are basically interested in the energy current, heat current that flows from the hotter reservoir to the colder reservoir, and what is the temperature profile along the length of this conductor, and so on. So there are many empirical laws, like Fourier's law is one of such laws which which tells you how this conduction happens and what is the current and so on. So theoretical understanding of these energy transport basically considers a Hamiltonian system which is connected to basically thermal reservoirs, which are, for example, Langevin baths, which are like equilibrium reservoirs with satisfying fluctuation dissipation theorem throughout. Okay, so the first analytical work in this regard was done in 1967 by Riedel, Lieb, and Lebowitz, where they considered a very simple system, an ordered harmonic chain connected to two Langevin baths at the two ends. So the Langevin baths are basically modeled by a constant dissipation and a fluctuating part, and a fluctuating noise, which is the Gaussian white noise, where the strength is actually proportional, related to the strength of the dissipation. So what you see here is basically this is the harmonic chain, and the two ends are connected to the baths, which are modeled by this red and blue parts, and the remainder of the chain is completely Hamiltonian, and they follow Newton's equations of motion. So what they found in this paper was that the average stationary current actually survives in the thermodynamic limit, and it's proportional to the temperature difference of the two thermal reservoirs, and the kinetic energy, average kinetic energy of each oscillator in the chain, that gives you the local temperature. And the average kinetic, if you look at the average kinetic temperature profile throughout the length of the conductor, you find that it's flat at the bulk, and it's just given by the arithmetic mean of the reservoir temperatures. These are all quite contrary to what is predicted from Fourier's law. And over the years, many generalizations of this model has been studied with pinning in the bulk, disorder, and harmonicity in the chain, and so on. But most of the studies in this respect has been with equilibrium reservoirs. So the forces that are there at that the bath end exerts on the end particles always satisfy fluctuation dissipation theorem. So now the question I'm going to ask today is, what happens if these reservoirs are out of equilibrium? And when I talk of out of equilibrium, so active particles have emerged as a paradigmatic example of out of equilibrium systems in the recent years. So active particle has already been introduced in the talk by Shraddha Mishra today morning. So they are basically self-propelled particles like bacteria, genus beads, and genus beads, which can dissipate and generate persistent motion. They're out of equilibrium, and they violate fluctuation dissipation theorem even at the single particle level. So advanced microrheology experiments in the recent years have allowed people to study the effects of a probe particle. If you put a probe particle in a bacterial or in a living medium, then what happens? What is the effective dynamics of this probe particle? So a lot of experimental and numerical activities have been carried out in this regard in the last 1 decade and so on. And unusual properties like negative friction, modification of equipartition theorem, and anomalous relaxation dynamics have been seen. So now again, I modify my question further. I will ask, what happens to the transport properties of an extended system when it is connected to two active reservoirs? So this is kind of a pictorial representation of what I'm going to discuss. So the first thing when I want to study this would be how would you, so thermal reservoirs were modeled, coupling to the thermal reservoirs were modeled by forces which followed fluctuation dissipation theorem. So how would you model the coupling to an active reservoir? So this is a simple model which was studied in this paper where you take an kind of independent oscillator model. So you have a test probe particle in between, which is this red one, and it is connected by harmonic springs to these black particles which follow overdamped active particle dynamics. So I modeled this active particle dynamics by just an exponentially correlated random noise, which is followed by the generic active particle models that you find, like run and tumble active Brownian particle or direction reversing active Brownian particle. So because of the linearity of these equations, you can integrate out the degrees of freedom of the bath, which is y, and then you can write down an effective equation of motion for the red particle, which is the tracer. So it turns out that the equation for the red particle is a generalized Langevin equation, where this is the memory kernel and this is the effective noise that is experienced by the red particle, which have these following forms. And if I take the strong coupling limit of this, so that is this coupling strength is much larger than the other parameters, so then basically it reduces to a Langevin equation, a normal Langevin equation with constant dissipation and an effective noise. So the takeaway from this is you can model the coupling to an active reservoir in the strong coupling limit by just adding a force which is related to the individual correlations. The correlations of this force and the constituent active particles of the medium are basically the same. And this also has been taken as a model in the previous experimental studies done in the past. Okay, so now we come to the model to study the activity-driven transport. So it is essentially the same model as the Ryder-Lieb and Lebowitz model, but now we have, other than this, the part coming from the thermal reservoirs, we have these additional forces F1 and Fn, which are exponentially correlated. And this tau j's, so tau 1 and tau n, basically these give you the measure of these are basically the characteristic time scales or the activity time scales, which basically is a measure of the activity of the system. So higher the tau j is, higher the activity of the reservoir. And again, the bulk oscillators follow Newtonian dynamics. And yes, so the system, because it's connected to two reservoirs, in the long time limit, if you look at it, it will reach a stationary state. And we are interested in this talk specially. I'll talk about the current that flows through the system in the stationary state and the average kinetic temperature profile of the conductor chain in the stationary state. Okay, so let's come to the results directly. So the average current that flows through the system, because it's a linear chain, it turns out that the average current that flows through the system separates out into a thermal part and an active part. The thermal part is exactly same, proportional to the temperature difference as in the RLL model. So I'll just take them to be zero in this for the following discussion. So if I look at the active current, what you see it begins from negative. It crosses zero, it becomes positive, hits a maxima, again changes sign, and then goes again to some constant value. So we actually can get an exact expression for the current in the thermodynamic limit of the chain, which is something like this. And so this non-monotonic behavior of the current is basically, so the x-axis of this is the activity drive. So basically what I do, I fix the activity of one of the reservoirs and I increase the activity of the other. So basically this it's some kind of a tau 1 minus tau n, if you consider that way. And this negative difference, so in one regime what you have is actually when it's decreasing, so what you have is you're kind of increasing the drive and the current is decreasing, which is quite counterintuitive. So this negative differential conductivity is actually a signature of non-equilibrium dynamics. It has been previously seen in systems with nonlinear in nonlinear models, and with models where there are different kinetic constraints. These are a few examples, but interestingly, the presence of active reservoirs causes this negative differential conductivity to occur in a linear chain. And I don't know. So basically, if we look at we've tried to look for some physical origin, but we were quite unable to find something. But what we can say is like this is some intermediate step in the calculation where we get some kind of an active Landauer formula where the system or the transmission coefficient, which is given by this basically your current is an overlap between this transmission coefficient and the reservoir frequency spectrum, which is nothing but the Fourier transform of the exponentially decaying autocorrelation. So the system spectra is basically peaked at the characteristic frequencies, which is proportional to the spring constants of the harmonic chain, while the reservoir spectra is a Lorentzian, which is peaked about the origin. And if you look at the overlap of them, you find that actually is non-monotonic. If you look at this plot carefully, so that is non-monotonic. So that actually contributes to the non-monotonicity of the current. And there's another interesting thing that happens in the current is it changes its direction twice. So what you expect is normally is like if you give a drive and then the current would be zero when the drive becomes zero. So there is one zero where the current is zero once when the drive is zero, but additionally there is another point denoted by these red dots where the current is zero. So there is this additional directional reversal. So if you look at the phase space of the phase diagram of the current in the activity plane, so you would see this diagonal is basically giving you the trivial zero when the activity drive is zero, and then this red solid line basically gives you the non-trivial zero where the activity drive is not zero but the current is zero. And the intersection of these 2 points is, if you just look at a straight line along this, passing through this point, along this or this axis, is a particular point where there is no reversal. So basically, it hits the zero line and comes back. So that also turns out to be a saddle point if you look at it in 3D. Yes, so now let's coming to the average kinetic temperature. So why are we looking at the kinetic temperature? So basically in equilibrium case, kinetic temperature calculating kinetic temperature would mean that you are calculating it gives you the local temperature at each site. So it turns out again that similar to the thermal case, the bulk profile is flat. However, there is a non-flat boundary layer which decays exponentially. Interestingly, the profile is not completely flat even when the activities are same. And the bulk profile can be calculated exactly in the thermodynamic limit, and it turns out it can be written in this form, which is the arithmetic mean of these two quantities, curly T1 and curly Tn, where curly T is given by this expression. So if you remember the expression for the average kinetic energy for the thermal case, it looked similar with this in place of this curly T's, it was the temperature at the two ends of the reservoirs. And this makes us ask the question that can we now have an effective thermal description for the chain, for this transport, where we can replace the active reservoirs by thermal reservoirs with these temperatures. So it turns out that that description is not consistent, because even if the activities are same, then the thing which we want to call some effective temperature, they are also same, but in that case still the profile is not completely flat, which is kind of a violation of the zeroth law of thermodynamics, because if the temperatures at the two ends are same, then it should be flat always throughout. So that's one check that does not satisfy. And of course, if you take the expression of the thermal current and you put this curly T1 and curly Tn, and then you see that the solid lines are basically the active actual currents, and the dashed lines are the active currents which we get by using this effective temperature description. So in general, you see that they don't quite match, but at very small temperatures, at very small activity parameters, you find that there is overlap, which basically this again follows from the exponential nature of the noise. Oh, that's a long time. Yeah, I'm almost done. So, basically, if the characteristic time scales are very small, so the exponential correlation in that limit basically reduces to kind of some delta function correlation. So this is again that same passive limit where actually an effective thermal temperature emerges. So I think that's all. So yes, so this is the summary. Basically, I studied energy transport. So this is all what I said. The important part from this is the results that I showed, the energy current and the temperature profile. So these results are robust for all kinds of active dynamics. So if I choose my active particle bath to be a run and tumble particle or an active downwind particle or anything, those results are robust. And the current and the temperature profile all follow that same behavior. And yes, but of course you would see the effect of the exact dynamics, and that is seen in the higher order fluctuations. So this is also, we have calculated them in this paper which was out very recently again. And we can further explore this by putting, I mean, all the studies that has been done in heat transport, like putting disorder and anharmonicity in the chain and etc. everything. Yeah, so that's it. Thank you.
For example, let's say you have some kind of a one-dimensional conduit.
One-dimensional?
Conduit or some kind of a one-dimensional channel through which you would want to actually communicate between these two parts. If there is an asymmetry between these two parts, would that still be kind of valid to look into such kind of arguments?
By asymmetry, you mean what?
For example, one particular part is at a very high temperature compared to the other one, which is also at a higher temperature compared to the first one. And
this will still, I mean, by temperature you mean the real temperature, or?
Yeah.
Yeah, I think this will still, so it will still work, because the model which says, I mean, you can just put the temperature in, the temperature is basically in the strength of these zetas, xis.
Yeah, is there something which also is dissipative on either side of the walls? That is what I am just...
So the dissipation is basically here, so
yes.
that's all. I mean, you can have any temperature.
You can represent, because there's also a dissipation through the chain, right? Through the...
There's no dissipation in the chain?
In the chain, okay.
Yeah, it's completely energy conserving.
But is that realistic, so to speak? Because there will be some kind of dissipation, right?
No, I mean, then, I mean, there can be dissipation. You can just model it by some momentum.
You just add one more part.
Yeah, I mean, inside in this one, yeah.
Thanks.
I have a question.
Yeah.
So there are some recent studies, also exact calculation for Ornstein-Uhlenbeck process in active scenario, and there the physics can be described by an effective temperature description. And let's say if you have to basically, is there a physical understanding of why it fails here?
No, there's, I mean, Ornstein-Uhlenbeck processes are a bit special. So I'll just show you one quick thing. So when we looked at the higher point fluctuations, so the velocity distribution, if you look at to characterize if it's equilibrium or not, you'd see that the velocity distribution of the Ornstein, if the bath particles are Ornstein-Uhlenbeck, it's always Gaussian. It's always the Gaussian, and it's always like Maxwellian. So.
So that
AOUP, I mean, that's special because AOUPs anyway you model by some Gaussian noise. I mean, it's one order more, but it's still Gaussian. So I think that's why its AOUP is somewhat special.
So,
yes.
Yeah, I didn't understand why. You had two zeros of the current, no? And you said one
there's
zero.
no physical explanation why that is, but it's just like that. Yeah.
Okay.
Yeah, so this is RRI where I come from, and this is like the Van Gogh form of RRI. Yeah. Okay.
Okay, thanks for this nice talk, and then let's rank.